Hi everyone, let's just go over a couple things that we built in class, but just to formalize them on your new quadratic family packet. Again, here are all 8 families we're going to study throughout the next couple months, and we're working on the linear family and the quadratic family kind of simultaneously since you're familiar with the algebra of both and you've seen both before. And like the linear family, the quadratic family has its own building blocks for an equation. So I think you're familiar mostly with standard form where you have ax squared plus bx plus c. And you can find the x-intercepts from this using the quadratic formula. I won't sing to you in this video. You also are somewhat familiar with factored form where you have x minus one of your zeros and x minus the other zero. When we worked with quadratic algebra, we spent a lot of time doing factoring puzzles with box method and setting up that quadratic puzzle x. And finally, something you're not familiar with that we'll build ideas in is vertex form of a quadratic. So all 3 of these are different ways to write or build a quadratic equation that we can graph. Looking at the parent function, the easiest form of a quadratic is y equals x squared. Remember, this is just a y equals, but we're labeling it f when we're working with different lines. So f of x equals x squared. And if I build the table for this, like you did in class, I can substitute in easy points. And what's really cool about a quadratic is if you can figure out where the middle is and put it in the middle of the table, it helps you cheat a little bit and take some shortcuts because, okay, so 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. If this is the vertex, then these numbers will all be symmetrical on this point, no matter what your vertex is. So over 1, up 1, over 2, up 4, over 3, up 9. What we notice is unlike a linear that just has a constant rate of change, and it either goes at a constant rate inclining or a constant rate declining, this rate of change actually changes. So there is no slope, there is no constant rise over run. So over here, it's important to read it left to right, but over here, if I read it left to right, the graph is going down. I'm sliding down the hill. And then here, I'm not moving anywhere. And here, I'm rising up, rising up, rising up. So my rate of change is less than 0. It's going down, negative. My rate of change is negative here. My rate of change is exactly 0 at the vertex here. And my rate of change is going positive over here. So I was able to label an example of each of these along my graph. The key features, like I said, there is not a constant rise over run, so it's not relevant. One of the things that we do talk about, though, that's kind of like slope is the rhythm of a parabola, the rhythm of a quadratic. And if we have an a value of 1, then the rhythm of the parabola will be from the vertex, over 1, up 1, over 2, up 4, over 3, up 9. Over 1, up 1, over 2, up 4, over 3, up 9. That is when the a value is 1. This is probably new vocabulary, the concavity. The concavity talks about how is the bowl kind of sitting. So this is a bowl, and the bowl is sitting up. So it is concave up. If it were upside down parabola, your concavity would be concave down. The x-intercepts and y-intercepts are things that you're familiar with. We can find the x-intercept by plugging in 0 for y. So if I put 0 equals x squared, the square root of 0 would just be 0. And our y-intercept happens when x equals 0. So if I substitute 0 in for x, 0 squared is 0. My x-intercept and my y-intercept, in this case with my parent function, both happen to be 0, 0. And we can see that on the graph right there. These might be a little familiar, maybe not. You've heard me talk about the vertex a couple times on that video, and that minimum or maximum point where it goes from, it has a change of direction, that's called our vertex, or minimum and maximum. And right now our vertex is sitting at 0, 0. And you'll also notice that parabolas are symmetrical. So this side, like we talked about in our table, is symmetrical to this side of the parabola if you split and kind of fold it at the vertex. And that axis of symmetry happens right here. And if we move the parabola right, it would happen right here. If we move the parabola left, it would, and that left-right motion is the x-axis. So right now, our axis of symmetry is happening at x equals 0, at x equals 0. And lastly, new vocabulary would be our domain and our range of what we're looking at. Domain, I always think about Lion King. If you've seen this, if you've seen the movie Lion King, there's a part where Mufasa takes Simba overlooking the land and says, it kind of explains that everything the light touches is within our domain. And so your domain is your left, right. So if I look on the graph, does the graph go all the way to the left? Does the graph go all the way to the right? Well, if I follow it, yes, 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 yes. And if I expanded my window, it would go all the way to the right, and it would go all the way to the left. Another way of thinking about the domain is there any x value that you could substitute in here where math would blow up? So for instance, let's try some weird numbers. Could you take 0 squared? Yes. Could you take -1 and square that? -1 times -1. Yeah, that works. Could you take a fraction and square it? 1/2 squared? Yep, that's 1/4. Okay, is there any way that I could get math to blow up with this equation? And I couldn't. That's really unlike taking a square root. I could make a square root blow up by putting a negative number within a square root, because no number squared equals a negative number. But in this case, I can't get math to blow up. So our domain is x can be anything. It can be any real number. And that might be new notation. X exists in all real numbers. It's just a really shorthand way of saying x can be anything. Last but not least, you have your range, and your range is your possible y values, the up and down motion. And for a parabola, your range will always start at your vertex, and it will either go up, above, or down below. So an easy way of doing your range is to write the y value of your vertex and then decide whether it's going to be above or below. In this case, the graph is going above the vertex, so it can be y is above or equal to 0, your up and down motion. So that concludes some pieces I want to talk about the basics. Notice we can have some weird quadratic functions that don't have any zeros, and thus we can't even write them in factored form eventually because they have imaginary y-intercepts. Here are 2 examples of parabolas we would not be able to write in factored form because they do not have their own zeros. So just some weird ones to pay attention to. You'll notice that a lot of the skills that will come up are familiar, but there are some ones like our rate of change being a little different in different areas that will be new. There's some discussion questions we're going to go over, but the big point I want to point out is you should always be checking your graphs, tables, and graphical solutions to your equation on Desmos, a friendly reminder for you. So the next video, I'll get into some of the puzzles.